So when we start into a lot of this and we start thinking in terms of maintenance, now um, let's talk about power generation in general and maintaining it before we get into grid infrastructure. So in power generation, I have coal, I have gas, I have nuclear, I have IBR style things. One of the nice things about the IBRs, though, is if I lose a turbine, when I have 120 turbines generating, each one generating, say, 2 megawatts or 3 megawatts each. So if I have 100 at 3 megawatts, it's 300 megawatts of power generation. And by the way, that would be a small wind farm. Usually, when you see them in the horizon, that's multiple wind farms closely brought together because of the wind structure for that area or the wind mapping that's done. So if I have a single turbine go out, it doesn't take out the whole thing. You only lose 3 megawatts of the total while that's being repaired. So I've seen arguments come in saying, oh, well, that occurs, so da da da. But there are still single points of failure in those systems. And the importance of single points of failure are just like we talked about in the grid. I can have all the power generation I want, but if a line goes down that connects that generation, uh, then I've lost everything. So let's talk in terms of the power generation first, because one of the things that has been talked about a lot has to do with the fact that with introducing different new sources of power, and the fact is that when I'm providing electrical power, it's basically I have to react to the demand. There's a limited amount of storage that's available, um, and therefore um, uh, I have to be varying my loads. Now, with a lot of the new um, uh, strategies that are being used, I end up varying the loads heavily on the large synchronous generation. What is the potential impact on that kind of situation with the new grid?
When you push large synchronous generators to ramp up and down frequently, you wear them out faster, like making a marathon runner sprint repeatedly. Thermal stress, mechanical fatigue, and increased maintenance follow. These plants thrive on steady operation. So if the new grid keeps asking them to chase variable demand, it hikes maintenance costs, shortens lifespan, and risks reliability. That's why a balanced grid matters. Letting flexible resources, like storage or IBRs, handle the swings allows those big synchronous plants to run more smoothly. In short, without balance, you burn out your workhorses.
Exactly. So, um, really, when we start looking at grid management, a lot of it is cost based because of the push to reduce end user costs. And then also, you have for a lot, I mean, when we went into deregulation on the power generation side, just so you're aware, in the US, the grid itself is not deregulated, just the power generation portion. So now you have all of the people that have invested in that power generation trying to maximize those dollars. So when we start looking at that, this causes us to effectively start doing things that reduce the life of the machine. It's not the fault of any one power generation type. It has to do with the models that we're following in order to do cost control, right? So this is a big part of the issue. And just as June just mentioned, when we're talking about inverter-based resources, they were always meant to be the top end, meaning because they're not dispatchable, they were meant to be that area to help keep the costs down by handling the variable loading. Now, variable loading is happening very rapidly. So let's get into the just quickly the next part. And I've heard the people say, well, look at those wind farms. It's windy out. They're not turning. There must be a problem with how they're maintained. They're not reliable. Well, why do they do that? What is curtailment?
Curtailment? It's not a failure, it's a choice. When the grid has more power than it needs, or when transmission is constrained, grid operators tell wind farms to dial back. It's like turning off the faucet when the bucket's full. It's all about balancing supply and demand. So when turbines aren't spinning on a windy day, they're often just waiting for the grid to need them. It's a tool to prevent overloading and keep stability, not a maintenance problem. In other words, they're reliable enough that we sometimes have to hold them back.
Okay, so On the other side of things, some of how costs are being controlled has to do with reducing maintenance. Now, there's certain maintenance requirements that are put forth by NERC and FERC and all the four-letter words, um, and as well as recommendations from EPRI, which is also a four-letter word. But that's neither here nor there. In any case, when we start talking about that, the impact, of those rules on maintenance, uh, if somebody does the minimum maintenance on a site, what ends up happening to the overall reliability and resilience of power generation and grid? Because we're going well over time, so I want to make sure that I cover both.
If you cut maintenance to the bare minimum, you're playing with fire. Short term, you save a bit, but long term, failures spike. You get more unexpected breakdowns, which cost more to fix and cause outages. For generation, that means lost capacity when you need it most. For the grid, it means more line and transformer failures. So a penny saved now is a dollar burned later. Real resilience comes from proactive care. Maintain both power plants and grid lines properly. Otherwise, reliability is just luck, and the lights or costs will reflect it.